Hello guys, hope you all are doing well. So in the continuation of previous GATE series, we are solving the questions of GATE 1990. So we have left with only two questions. So we will discuss here. So without wasting time, just we will solve the question. So what question is saying? It will be visible to a screen. A irreversible homogeneous liquid phase reaction. First I will write GATE 1990, and this question is from CRE and specifically ideal reactors. Ideal reactors combination. Okay. So and sorry, irreversible uh, irreversible homogeneous liquid phase reaction. So we have a liquid phase reaction A that gives B plus C, and we know that for a liquid phase reaction expansion factor is equal to 0. So we don't assume that there is a volume expansion, okay, because it is 0. Is carried out in two isothermal flow reactors. Hence the condition is isothermal, so temperature will remain constant. Of 100-liter capacity each operating at 60 degrees Celsius. Volume of both reactors, volume 1 100 liter, volume 2 100 liter. Find exit conversion if both the reactor operated in series. So we have to find the exit conversion, that is X2, because the conversion after the second reactor, X2. We have a condition A. If both are PFR, and B, both are, sorry, PFR followed by CSTR. Okay, so without going into the question, we have some values given in the question. We have here, I'll write VA naught is equal to 20 liter per minute, CA naught is equal to 1 mole per liter, okay, and K is equal to 0.5 minute inverse. That means the reaction is of first order. So rate equation will be minus RA is equal to KC, right? I'll write it as K C naught 1 minus X. Okay, hope you all understand this. This is very basic in chemical reaction engineering. Without going into the question, we will see the profiles of both the reactor when they are connected in series. Different reactor connected series. So first we have the PFR. Both are PFR. Okay, both are PFR. Both the reactors are plug flow reactors. This is V1, and we have another plug flow reactor of volume V2. Okay, connected in series in the first part. So the profiles of this, hope you all know from where this graph comes. Okay, this is the basic graph in the ideal reactors. Okay, so if I consider volume 1, so for V1 it will come here, and for V2 it will come here. This is the graph for plug flow reactor. This is the graph for plug flow reactor. Okay, this is the graph of plug flow reactor. Okay, here it is minus 1 upon R, and here it is X. Okay, conversion. So this is X1 and this is X2. So see, if I will solve, if I will perform, so see, if I will apply performance equation of PFR individually for this reactor and for this reactor, I will get X2. Right, I'll surely get X2. Some value will be there. If I will apply in the first V1, In the first reactor, I will apply performance equation once. Then in the second reactor, I apply performance equation twice. But see from the graph, if I will add the volume of both the reactor, that is V1 plus V2, I will get the same conversion if I will solve the individually. See, if I will solve, if I will apply performance equation once here, and then I will perform and apply, then I will apply performance equation once here, I will get x2 if I will calculate individually. But if I will add the volume of both the reactors, if I will add the volume of both the reactors, I will get the same conversion as x2 here. We will see that. Okay, I'll calculate from both the ways. Okay, so part A. So we have V naught. Okay, so applying performance equation of ideal PFR. Okay, we will solve from both the ways. So first I will apply for reactor 1. Okay, V1 upon V naught performance equation, we know that tau is equal to V1 upon V naught is equal to V upon FA naught upon CA naught. Sorry. V CA naught upon FA naught is equal to CA naught dXA upon minus RA 0 से XA. Okay, this is the performance equation of plug flow reactor. Okay, so we will use V1 upon V naught is equal to CA naught dXA upon minus R. Okay, we are using for first reactor only. So first reactor volume is 100 liter. V naught is 20 liter. We will not forget the unit, right? We will write the unit along with the numerical value. CA naught. Why I am not writing the value? You will get to know. K CA naught. CA को what I can write? Rate is KCA, and for CA naught 1 minus XA, right? So 1 minus XA. So CA naught will cancel out. Okay, so here liter will liter cancel out. Okay, and 5. So 5 minute into 0.5 per minute. Per minute means value of K, minute inverse is there, is equal to integrate this dXA upon 1 minus XA. You will get minus ln 1 minus XA. I want to give you a tip here. Don't leave this part like you will solve in the real exam. You are giving the gate exam and you are solving this the integration. Always remember the values of these integration. dXA upon 1 minus XA, 1 minus XA. Okay. Always remember the values of these three. Always 1 minus XA का whole square dXA is equal to under root 1 minus XA. Okay. Always remember the values of these. It will save much time. Okay, it will save your time in the examination. Just write it directly. I have learned all the values of these three, right? So because in exam the time is very less, right? So minute will cancel out 2.5 here, minus ln 1 minus xa. I will write it x1 because it is the exit concentration from the first reactor. Minus 2.5 e की power is equal to 1 minus x1. So x1 will be 1 minus e की power minus 2.5. So x1 will come as 0.9179. 0.9179. Okay. Now applying the same performance equation again on second reactor. V2 upon V naught is equal to Ca naught. Now this time not from 0, x1 to x2 dxa upon minus Ra. Right? What we will get? V2 is 100 liter again. V naught is 20 liter. We will not forget the unit. Minute is equal to Ca naught and Ca naught will cancel out. So this will become x1 to x2 like this, minus ln 1 minus xa limits x1 to x2, right? So here liter and liter will cancel out. Okay, I forgot the k, so k will be here. I will just write k. Okay, so 2 2 2 5, so 5k, so 5k minus ln 1 minus x1 to x2. Okay, 5 into k is 0.5 minus ln, I'll send this minus here, 1 minus x2 minus ln 1 minus x1. x1 we have just calculated when we applied the performance equation on first reactor. So minus 2.5 is equal to ln 1 minus x2 upon 1 minus 0.9173. I think so, right? 9179. So I just use the log property here from this step to this step. I just use the log property. If you don't know, just learn it. Okay. So from here, x2 will come 0.9932. Okay, 0.9932. Now, let us add the volume of both the reactors. V1 plus V2 upon V naught and applying the performance equation of CSTR, Ca naught 0 से x1 x2 we are just adding, so we will get at the end x2 0 to x2. Okay, dxa k Ca naught 1 minus x. Ca naught will cancel out, it becomes 200 liters. Okay, and minute liter upon V naught is 20 liter minute into k, okay, equal to minus ln 1 minus x2. That's all. So minute will liter cancel out, minute will cancel out. Okay, so 10 into 0.5 minus e to the power is equal to 1 minus x2. So from here x2 is 0.9932. See, the same value is coming and the number of step is 1, 2, 3 tests. And for that one we have calculated first for volume 1, reactor 1, then for reactor 2, and automatically we are getting the same answer. Okay, so always remember when it comes to PFR, it will give the same volume when we add all the volumes of small PFRs. Okay, PFR followed by CSTR, followed by CSTR. Always go for the profiles. You will know and easily understand what you have to do in the question. So this is the basic profile. So PFR followed by CSTR. We have to always, the purpose, I will tell you the purpose of combining these different type of reactors. The purpose of combining all these reactors is to minimize the volume of the reactors. The minimum volume will be the best alternative. Always remember, minimum volume will be the best alternative. Okay. So because per volume the cost is very high. Okay, and the cost optimization of every industry is first priority. Okay. So PFR, for PFR, if I will get first I'll, this is PFR, and then it is going to CSTR. Okay. X naught, which is equal to 0. X1 has some conversion which is going in the CSTR, then X2 we have to find. Okay, and this is PFR of volume 1 100 liter, volume 2 100 liter. Now for first, suppose I get X1 here, I get X1 here. So for PFR, this is the profile. This. Okay, and for CSTR I have the profile like this. Okay. Okay. So here we can't do anything. We have to solve individually. Okay. We have to solve individually. So in the first question we have calculated that X1 will come exit of the PFR 0.9179. Right. Now applying performance equation of CSTR. Performance equation of CSTR. So for CSTR, tau is equal to V by V naught is equal to CA naught XA upon minus RA. XA minus X naught हाँ अभिषेक हेलो हाँ अभिषेक ठीक है मैं लगा दूंगा हाँ ठीक okay. So we applied the performance for CSTR, and here you see that XA minus X naught for XA minus X naught. Okay, now V by V naught is equal to CA naught. In this reactor, X1 minus X naught. X1 is X2 and X naught is X1. How? When you apply performance equation on single reactor, this is X naught and this is X1. Exit concentration is X1. Exit concentration always comes first and inlet concentration will be after. So I have write this is a general equation for only single CSTR. So applied here for single CSTR, but the notation is different here. For X1, exit concentration is X2 and inlet concentration is X1. Okay. K Ca naught 1 minus Xa. Right? Ca naught will cancel out. Okay, we have volume 100 liters upon 20 liters per minute. Minute will go up, is equal to x2 we have to calculate. X1 we have calculated this output conversion of PFR 0.9179 upon zero point 0.5 minute inverse into 1 minus x2, right? Liter 25 5 into 0.5 2.5 and minute will cancel out. 2.5 is equal to x2 minus 0.9179 upon 1 minus x2. Okay, so 2.5 1 minus x2 is equal to x2 minus 0.9179, right? So 2.5 minus 2.5 x2 is equal to x2 0.7197. 2.5 plus 0.9179 is equal to 3.5 x2. 2.5 plus 0.9179 upon 3.5 is equal to x2. 2.5 plus 0.9765. 0.9765. So this is the final answer. Okay. So hope you understand this concept. So if you have any problem, just comment it below. I'll try to reply as soon as possible and stay focused. Okay. And bye guys. Take care.